So, welcome to our review of Chapter 2. I have a few announcements to go through at the beginning before we launch into the problems. On Tuesday, I asked that if you had any specific problems you'd like to see, let me know. I appreciate that 2 people actually did send me messages, but one of them came in this morning. Luckily, I had already created a problem that, like what they were asking about, because at that point it's a little late for me to start. So if you can, send me the questions at least the night before so I have a few minutes to put something together to talk about for you. Okay, let's go back to sharing and okay, I assume you all can hear me okay? Yes?
Yep.
Okay, good. All right. So some announcements. So as you may know, Practice Quiz 2 does not cover all the material that you need for Quiz 2, nor is it the same length as Quiz 2. I already suggested a bunch of problems in the book for you to have a look at, and you're welcome to ask questions about anything you don't understand once you give it a try. The quiz is exactly 1 week from today at exactly this time next week. Remember, you have until 12:35 by the Gradescope timer to finish and upload that exam. So I urge you not to wait, not to spend all your time during the exam, plus during the extra time for uploading, because you don't want to run out of time. The templates will be available 1 day ahead of the exam on Wednesday, February 17th. You have to read the rules and abide by them. If you have a serious problem with submission before the Gradescope timer goes to 0, you can submit by email as the rules instruct. Now, the rules tell you exactly to whom to send in an email the exam, as well as your excuse about why you couldn't get it in. And so it's an email. It is not through Canvas. It's not through Piazza, and it's not to me. It's to one of the TAs. So read the information again and again. You have a sample that should be correct, but double check it. Make sure you've got that right. You can do all of that before the quiz starts. Okay. Writing the quiz by hand is probably faster for you than trying to type it into LaTeX or Word. So my suggestion is, if you were short on time last time, I am taking your issues about length into consideration making the exam, but still you want to give yourself the most time possible. And to that end, I suggest that you print out the template in advance, sign the pledge, read the rules, and be ready to go when Gradescope allows you to see the quiz, download, or whatever. Do not write the questions on your solution pages, okay? Write your solutions. We don't need to see the questions again. We know what they are. If you need to see them while you're solving it, then print out the quiz questions, and then at the top of your page, have the quiz question that you're working on right above it so that you know which one you're working on. But you do not need to spend your time writing or printing it. That's too much, takes too much time. Don't do it. As long as your solution is, your handwriting is legible, it will count as much as possible. If we can't read your solution, or it's all over the page because you didn't know what to do, that's hard because we can't follow things. So if you start going all over the page, take a clean sheet and use that as your template, write the question number you're answering, and when you upload and submit that instead of the one you printed out from the template. Okay. Be sure and follow the proof templates as much as possible that we went through. For example, we went through what a direct proof does, what you do in a contrapositive proof. A contrapositive proof is it's an indirect proof, but what you do is you do a direct proof for the contrapositive, and it's an indirect proof of the original. Similarly, a proof by contradiction is an indirect proof because you're proving that something cannot happen, so the original is correct. Kyle, what's your question?
So for the proof by contrapositive, once you prove the contrapositive, is it enough to just say because the contrapositive is logically equivalent, therefore the other one is true as well?
Absolutely.
Okay, thank you.
That's exactly the right thing to say. Okay, so now the question is, what are the theorems or propositions that were in the book or proved in class or on the pre-recorded videos that you can use without proving on the exam? The answer is not many. The division theorem, the fundamental theorem of arithmetic, and the pigeonhole principle, unless you're specifically told on an exam question that it's okay to use a certain result. Okay? So it is possible as part of your proof, for one thing, you may need to prove one of the things that you know from class. So go over those proofs, figure out were they done this way. So if you do have to prove them, then that question will be worth more points because you're doing a subproof as well as the original. So you should be able to knock those out cold since you've seen them, you've studied them. I'm hopeful that you can at least. Okay. It is certainly okay to use all our properties like closure under multiplication, addition, subtraction of integers, like associativity, commutativity, etc. You might be asked to prove such properties for rationals because we improve them. Okay, last announcement. We have set up 2 review sessions for you. The exam is on, oh, I'm sorry, Christopher, you had a question.
Hi, just to be clear, so for the proofs, we would not need to list the propositions themselves, right? Just the proof.
I'm sorry, I don't understand what you're asking me.
So on the quiz, we don't need to list the proposition that we're trying to prove, just the proof itself, correct?
Well, you have to say what you're trying to prove, and that's the proposition. So for example, if you're trying to prove if n squared is even, then n is even, because you need to use it, then you have to say what you're proving so we know. Okay?
Okay, thank you.
Otherwise, it sort of looks like it's something out here in right field, left field, whatever it looks like to you. Okay? So if you know what you're trying to prove, you should be able to state it really succinctly. There will be nothing that you're supposed to prove that was done in class that's long and odd and weird. Okay?
Okay, thank you.
All right. Review sessions. We've set up 2 of them, and this time they're at different times. There's Monday from noon to 1 o'clock. That's just a 1-hour review session. And that's with James during his office hours. So look up when you want to go to it, go to the weekly office hour calendar and look up his Zoom, the Zoom link that he's got there and the password so you can go, and that's it. The other one is Tuesday from 5 to 7, and that's with Nancy. Okay? And that also, you have to look her stuff up. We will also try, for those who can't make either one of them, to stream them and leave them there so you can watch them later. And obviously everyone can watch them later. Okay, and they'll be labeled review sessions. So there'll be 2 different ones on 2 different days. There will not be a review session Wednesday night, so study early. Okay? There will be regular office hours on Wednesday, but nothing labeled a review session. Okay, so this weekend, study. Okay, we will try and have your homeworks back to you in time to look them over, to double check them. But once they're handed in, if you have questions about a solution, go to office hours and ask questions about them. Okay, once they're handed in, that's fine. Okay. Are we ready to launch in? Okay, our first practice proof is one that says prove that the square root of 2 is irrational. It's in Q prime. And here I'm saying you can't do contrapositive. I'll give you some hints because it's no if-then statement. So you can't do not then implies not if there. So that's not something you can do. And the second thing is that it's really hard to prove something is irrational. So what do? Well, that's a contradiction proof. So I'm going to give you a few minutes to try it yourselves, and then we'll launch in. So give it a try. So someone asked earlier, I didn't catch it, that what was the reasoning? What is the domain of Q here? Q is the rationals and Q prime is irrationals. Someone asked, what's the reasoning behind not including all of the types of material that would show up on a quiz too, on the practice quiz? Well, let's see. In terms of the kinds of questions that we ask, you have all the examples that are done in the book, all the examples that are done in the pre-recorded lectures, all the examples that I do in class. And it takes a lot of time to think of examples. And then making up the real quiz takes a long time because I have to think of examples that are, or problems that are not too hard and not too far away from the kinds of things that we learned in class, but not too easy. And it takes a long time to make up an exam. It takes a lot of effort. So making up practice quizzes after all the other things, is very hard. Okay. So that's the reason that there are some problems on it. But I could say, go back and look at everything that we did and try and do them, which I tried to take, but that's not the practice quiz. So I guess I consider the practice quiz just some extra problems, additional problems for you to see how fast you can do them. Okay, should I not call them a practice quiz? I can call them practice problems. Okay, going onward. Let us go onward and look at this proof. So I'll take contributions from the group. What should we say that we're going to show? What's our hypothesis if we can't say P and not Q because we don't have a P? We're going to suppose not Q. Sorry. So we're going to, oops, too heavy. Suppose, when I say not Q, we're going to suppose the square root of 2 is rational. Okay, so we're going to suppose the negative of what we want to show and show that that's impossible. Okay, So by the definition of rational, that's too heavy for me. Definition of rational, the square root of 2 is equal to a over b for a and b in Z. You can say there exists a b such that the square root of 2 is equal to a over b. Okay? Suppose a and b are relatively prime. We can always suppose that, because if they're not relatively prime, we can by the fundamental theorem of arithmetic, each one can be factored into a product of its primes, and we can factor out every prime that they have in common. So at that point, we're assuming they're relatively prime. So what's the next step? Well, the next step says that then a is equal to b times the square root of 2, or a squared is equal to 2b squared. Now, can you remember the problem we did Tuesday? Tuesday, we showed that there do not exist integers a and b that are relatively prime such that a squared is equal to 2b squared. And so we could just cite that, but if you want, we can redo that proof through this one. Which do you want to do?
Redo.
Let's redo it.
Redo.
Redo it? Okay. So what do we know here? Since we have a divisor of 2 on the right, that implies that a squared is even by the definition of even. Okay. And then that implies that a is even by the proposition that we could prove, if it were a test, that if a number squared is even, then the number is even.
If we wanted to use that on a quiz, could we just, do we
Nope,
have to
gotta prove it? Got to prove it. If you want, we'll do that on the side in a minute.
No,
Yeah,
that's
can
fine.
we redo it?
It's easy.
I'm sorry?
Can we redo it?
Redo, what do you mean, can you redo it?
Sorry, can we redo the a equals a squared proof?
You mean if a squared a doesn't equal a squared. If a
Yeah,
squared
sorry.
is
The a is even proof is what I mean.
if a squared is even, yes, we can redo that in a minute. Let's finish this and then go back and prove that, okay? So what we have is that implies a is even. So then a is equal to 2k. So a squared is equal to 4k squared, which is 2b squared. And that implies that 2k squared is equal to b squared. And what does that tell us? That tells us that b squared is even. This is by the definition, by def of even. And again, by the same proposition, by proposition, that implies that b is even. Okay, if a is even, let me say since and b is even, they are not relatively prime. And that's a contradiction. Okay, so the square root of 2 is in the rationals. You can see how that little proposition is really handy. Okay, now we can prove that little proposition. Prove that n squared even implies n is even. Okay, we're going to just proof by contrapositive. What does that say? N odd, if it's not even, it's odd, implies n squared odd. Okay, so let's say, suppose n is odd. If n is odd, there exists k in the integers. It's a k. Such that n is equal to 2k plus 1. So we square it. N squared is equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1, which is equal to 2 times c plus 1, c equal to 2k squared plus 2k is an integer by what? Closure under multiplication and addition. Hence, n squared is odd. And that's the proof. Since we have proved, I can't fit it in here, but then there's that last statement that someone asked me about. Since we have proved the equivalent contrapositive, the original implication is true. That's that last sentence that closes it all up. Yes, David.
Yeah, I was just wondering how we get the suppose A and B are relatively prime. Like, what determines what we can say there and what we can't? Like, because I couldn't just say suppose A is root of 2 is irrational. Like, how do we get sentences that we can say suppose this? Like, because like, you see what I'm trying to say there?
Typically, yeah, that's a good question. Typically, what you're doing when we say suppose or assume, you're saying assume the hypothesis is true. Okay, so the first statement here, we're assuming that we hypothesize the square root of 2 is rational. Therefore, there exist integers a and b such that the square root of 2 can be written as a over b. You also know from something else that you can assert, I can't remember what it is, that every fraction has a relatively prime form. Now, at the beginning of this, you may not know that you need a relatively prime form, but you go through it and then you're going to come out with something that you don't see quite as a contradiction down here. You get the fact that they're both even. And if, unfortunately, if you don't assume they're relatively prime, you're going to have to keep factoring out stuff. So you get to that point and say, you know, this is sort of a roundabout kind of thing. We start out here and we say, well, we have that a squared is 2b squared. And down here, you get that b squared is 2k squared. So what you want to do is at that point say, you know, I got these evens here and I want to somehow figure out that that's the contradiction. And the only way you can do that is if they're relatively prime. So if you didn't say it at the beginning, then you go back and say, well, assume they're relatively prime. And then you come back down here and say, see, that says it's a contradiction. Okay, it's okay to do that. You might have to put a little caret and say, assume they're relatively prime in your solution. That's okay. Okay? All right. The key is to recognize when you want to have the contradiction occur. Any other questions? Dane.
Sorry, it took a sec to get my microphone on mute. So if we happen to get stuck on the quiz, do you have any advice for scrambling to try and figure something out?
My first advice is if you get stuck on a question, go on and do other ones. Sometimes you get yourself into a rut and you can't see something. And if you go do the rest of the exam and come back, sometimes the difference in perspective, you may have seen something in one of the other questions and it becomes easier to see. Okay, so that's the first thing. Don't grind out this problem forever because you use up all the time you could be answering other questions and getting more points. So that's the first thing. The second thing is if you come back to it, you're done with everything else and you still can't figure it out. What I would tend to do is take a deep breath and say, maybe I started down the wrong path. Okay, what else do I know? What's given to me? What am I hypothesizing? What can I make assertions about? Because sometimes, like you might try and go a direct proof when you just get wound up and you can't get any further. Or you might try a proof by cases and you pick the wrong cases or something like that, okay? So it's to take a deep breath and go back and look at it and say, what is this telling me?
That's helpful. Thank you.
Okay, but don't waste all your time on one problem. You know, spend up to half the time you've allocated for that problem. And if you can't get anywhere, go on so that you still have time to come back to it at the end. Okay? All right, next practice proof. Among, this one you may notice I've got, among any 7 positive integers, there are 2 whose sum or difference is divisible by 10. I just noticed that that was on the pre-recorded. I didn't realize that in advance. Do you want me to do this anyway? Because it was in the pre-recorded video, I think, review.
Yes.
That's
Do
a
it.
yes, you would like me to do it?
Yes, please do it.
Okay. So why don't I let you give it a try to start with, and then we'll jump in. Let me give you a clue. Okay. When it says among any 7 positive integers, there are 2 whose sum or difference, that immediately says pigeonhole property. Okay. So then your key is to figure out what's M, what's K, what's N, and then how to label them. Stefan.
This is a question from the chat. It's not actually mine, but I kind of want to know the answer too. If we're given a hint, like on the quiz,
Yes.
do we need to prove the hint? Or can we just assume the hint is true?
If you're given a hint on the quiz, you'll usually be said, you may use that blap. And that says you can use it.
Okay, thank you.
Dane.
Oh, I'm sorry. I forgot to lower my hand.
Okay. All right. Well, let's start on this problem then. So what's the key? Somebody give me a helpful hint. Well, anybody want to give a hint?
We
How
need
many
to have,
objects are there?
there are 7 objects.
7 objects. Okay. k equals 7. What do you want m plus 1 to be?
2.
2. Right there. So we've got 7 and 2. So we know that 7 is equal to the number of boxes, bins, pigeonholes, times m. Well, if m plus 1 is 2, m is 1 plus 1. So the number of bins is equal to 6. Now, we haven't used anything about being sum or difference divisible by 10 yet. Right? So now we know we have 6 boxes. Now, how are we going to label them? Here's where the divisible sum or difference divisible by 10 comes in.
I'd label them based on the last digit, 0, 1, 9, 2, 8,
Yes.
etc.
So here we're going to use that. How are we going to use it? That's the division theorem. We have where we're dividing by 10. Dividing by 10. Okay, so that's the first thing. You're going to use the division theorem. Since you have only 6 boxes, you can't have a separate box for everything in order to get 2 in there. So what we have to do is say, okay, how are you going to label them? And how did you decide to label them 0? What was it? 0?
0, and then I was thinking 1 or 9.
Why?
Well, because 1 and 9 equals 10.
Yes. So what we're going to do is we're going to label boxes by the remainder R and 10 minus R. Why 10 minus R? Because if we add R and 10 minus R, we get 10. So the sum will be divisible by 10. Okay, so this is going to be remainder 0, remainder 1 and remainder 9, remainder 2 and remainder 8, remainder 3 and remainder 7, remainder 4 and remainder 6, remainder 5. Because 10 minus 5 is 5. You get the same thing again. Very good. All right. Now we've labeled them. Now we have to prove it. We haven't proved it yet. So we have a bunch of cases here to prove. So the first case is if there are 2 in the box with remainder 0. Well, if there are 2 in the box with remainder 0, then number 1 equals 10 K1, and number 2 equals 10 K2. So if I add them, I'm going to get 10 times K1 plus K2, and that's certainly divisible by 10 and has remainder 0. Okay, so certainly divisible by 10. If I subtract them, they're also divisible by 10. So this is a nice case. The next easy one to do is if it's remainder 5. That's a single remainder by itself. And in that case, N1 will equal 10 times K1 plus 5. And N2 will also have to equal 10 times K2 plus 5. So again, if I add them or subtract them, I'm leaving the rest of the work to you because I don't have room here. But if I add them or subtract them, I see that I'm going to have 10 times some sum or difference, and the 5s will either add to 10 or subtract from each other and be 0. Okay? The last case is the most interesting case. Okay, so the last case is when I have 2 in one of the remainder bins that's not 0 and not 5. Okay, so then there are two things that can happen. Either both of the numbers have the same remainder, or they have different remainders. And I have to prove for each case that I get the right thing. So if they both have the same remainder, so let's do that. We'll do same remainder here. In that case, we have number 1 is equal to 10K1 plus R, and N2 is equal to 10K2 plus R. So N1 minus N2 is equal, I'm skipping a couple of steps here, 10K1 minus K2 plus R minus R, which is 10 times K1 minus K2. And then what do we do to complete that? We say that's equal to 10 times C, where C equal to K1 minus K2 is in Z by closure. Okay. The more interesting one is remainder. There are different remainders. Let me do that up here. Different remainders. In that case, we have number 1 is equal to 10K1 plus R, and N2 is equal to 10K2 plus 10 minus R, because that's how we picked the bin. So now what do? Do we subtract or do we add?
Add.
Add, right. So N1 plus N2 is equal to 10 times K1 plus K2 plus 10 minus R plus R. So that's equal to 10 times K1 plus K2 plus 1. So I'm doing the distributive property, and above I already did the distributive, and I used commutative and distributive properties. You should put all the other steps in, but I did not leave myself a blank slide to get everything in. Okay, don't forget all those steps. Don't forget commutative, don't forget associative. You need them. Okay. Is this one clear to everybody now? Yes, James.
A question that I've seen based on all of our example questions up to this point is that for most of these pigeonhole principles, we're just proving the claim. But I was wondering if the pigeonhole principle is equally applicable to contradictions, and if going through these steps, we are thereby disproving the contradiction. I guess another way of asking this question is, we're relying on the fact that the sum or difference is divisible by 10. But if we were to say the sum and difference is divisible by 10, this proof would fail.
That's because it's not true.
Exactly. So are we ever going to be asked to show that a pigeonhole principle as presented is not true?
Oh, wow. You mean that if you apply it, you come up with an untruth? I don't think that's feasible. There is another more general pigeonhole principle than what we had there. So for example, let's look at this problem here. Suppose you had 8 positive integers and the rest of the problem read exactly the same. Okay. Then you would sort of scratch your head and say, I can't do it. There's nothing. I can't get it into the form k equals n times m plus 1. Okay. The pigeonhole property still applies to something like that, because a more general statement of the pigeonhole property that we didn't have any of you ever seen the ceiling operator?
Yeah,
Okay.
it rounds up, except like 2.1 goes up to 3.
Yeah, the ceiling operator says that if I take k and divide it by n, the number of, then that's equal to, so what we have is k is equal to nq plus r. That's the division theorem. And this, the ceiling operator says that's equal to q if r equals 0 and q plus 1 for r greater than 0. Okay, so in this particular example, we had k was 7. N was, we're going to show, we want 2 where m is 1. So this can be m. And then what you end up with is something that says 6, because it'll be 6 with the remainder of 2. So that says, I'm sorry, it's 1 with a remainder of 2, and that says 2 boxes. So it's a more general statement of it. So you have to be careful if you're assuming it fails, because you have to know the more general one. So will I give you something that's a trick question? I try not to.
Thanks. I appreciate the clarification.
Okay. Oh, I did have an extra one. Okay, let's fill in the missing details of this proof. Okay. Give it a try, and then we'll fill it in. Okay, let's do it, and then you'll have your break. So the first case says here that what we're trying to prove is every prime number greater than 3. Remember what a prime number is? It's any integer larger than or equal to 2 whose only divisors are 1 and the number itself. So that number itself is its own prime factorization. Okay, so the first thing says that any number greater than 3 has a square that's of the form 12k plus 1. So what we're going to prove is that it cannot have any other form. Okay, so this is a contradiction and cases proof built in together. So the first thing we say, well, if you divide by 6, suppose there's no remainder, then 6 divides n. Why can't that happen? Why can 6 not divide n?
Because
Because it's
6
prime.
itself is
Because it's a prime.
divisible. Yes.
And the rest of the statement. And then we have, suppose n is equal to 6q plus 1. Then n squared is equal to what? Well, 6 times
36q squared.
Yes, 36q squared plus 12 times 2q plus 1. And what's that equal to? That's equal to 12 times 3q squared plus 2q.
Wouldn't that just be 12 times q in parentheses, not 2q?
You are so right. Thank you. How's that? Thank you.
Yep.
Okay. So what's the next statement? Well, that's equal to k. We can't have k now. 12, let's say a. So that's 12a plus 1, which is exactly the form you want. So that's not a contradiction. That says, yes, it's possible if n has the form 6q plus 1, then its square has the form 12q, 12k plus 1. What about n equals 6q plus 2? What do we get? Why can't that
Even.
happen?
Because then it'd be divisible by 3 if you factor out a 3 there.
Well, if n is 6q plus 2, it's divisible by 2. You got the next one to tell me that. N is prime. So it can't be divisible, can't be even, and greater than 2. What about now? Tell me that reason why it can't be 6q plus 3.
Because it can't be divisible by 3.
Yes. 3 divides 6q plus 3. So that isn't prime. What about 6q plus 4? What's wrong with that?
Same
answer is
6q
2.
plus 2.
Say that again.
The same as 6q plus 2.
Same as 6q plus 2, yes. Since then n is even, greater than 2, can't be prime. What's the next one? What about 6q plus 5? What's n squared then? Well, it's 36q squared. And then what do we have here?
Q plus 2.
Huh? I have 6q times 5 is 30, and then again is 30, that's 60, and that's equal to 12 times 5q plus 1. So that's all equal to 12 times. Check my arithmetic.
Wouldn't be plus 25.
What would
Well,
be
it'd be
25?
plus 24 because you're taking the 1 away. So it'd be 5q plus 24. Or, sorry,
Oh, there,
5q plus 2.
plus 25. Okay, so we're going to do it here. We're going to do that here. So then that's equal to 3q squared plus 5q plus 4 plus 1. So it's 12c plus 1, where c is equal to yada, 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 which is true for closure. And then it has the same form. So it is possible, this case is possible, and this case is possible for a prime number greater than 3, because then its square is 12k plus 1. Notice that does not say that if a square of a number has the form 12k plus 1, then the number is prime. That would be the converse, and that is not the assertion. A converse is not equivalent. Remember that. Yes, Fabe.
Oh, I was thinking it should shouldn't it be 2 instead of 4 inside the parentheses?
Yes. Wow, my arithmetic is terrible. I appreciate it. There, thank you. I'm glad you're following so long as tightly that you catch it. Thank you. Okay, break. You can ask me anything you want in the next few minutes because it's break time. You can go off, have a drink, whatever, of water. Grant. Yes.
I feel like this is probably pretty obvious to some people, but why are the remainders only up to 5? Like, why is it divided by 6?
That's an excellent question. That's an excellent question. You can divide by anything, okay? But this is the case that is easiest to show because you're saying something of the form 12K. And you say, well, why don't I then divide by 12? Because if you divide by 12, you're saying the square has a 12K in it. So you can divide by anything. You just have more cases to show if you divide by 12. Okay, so why don't you divide by 2? Well, you know that the number has to be bigger than 3. So 2 and 3 is 6. You may as well try that.
Oh, I see. Okay, that
That's
makes
an
sense.
excellent question. Yu. Do I pronounce your name right?
Yo-yo.
Yo-yo, sorry.
Just want to ask, do you suggest to gather all the, because we can use all the theorems and propositions from the book, right? So do
You
suggest...
cannot. What I said earlier, perhaps you came late, is that you can only use the division theorem, the fundamental theorem of arithmetic, the pigeonhole principle, and the properties of integers. The rest of them you should know how to prove. Okay, I could ask you as a sub thing to prove one of them. For example, if n squared is even, prove that n, use that n is even. If you want to use that, you could be asked to prove that.
Okay, so
you should know the propositions so you know what to use, but study, you have a whole week now, try and study these propositions so that they make sense to you and look at the proofs. That proof, we did that proof here, somewhere. Here, not that one, here. So here's where we proved that if n squared is even, n is even. It's not a long proof, and it's a contrapositive, proof by contrapositive. Similarly, you can prove if n squared is odd, then n is odd. You can also...
So what about those theorems? Can we use them or not?
What theorem other than the division theorem and the fundamental?
I'm just saying like those theorems. We can just use them directly, right?
I'm sorry?
I'm just saying those like division theorems, we can use them directly, right?
Yeah, the division theorem you absolutely can use. If you have a question about a different one, send me an email. You can ask. Put a question on Piazza, and then I can reply to everybody at the same time.
Okay, thanks.
Okay, Christopher.
So what you said about the cases in the last proof, could we have just gone up to remainder of, would it be 3 or 4?
Well, we'd have missed something. No, you can't do that. You have to do all of the remainders, because the reason you can do this is that you know that every integer has the form. So if you divide by, the division theorem says that you can write any integer n is equal to, what did you have? The divisor, I can't remember what it was called, b times the quotient plus the remainder, where 0 is less than or equal to the remainder is less than b. If you don't do all possible remainders, you haven't proved it for all possible integers. So you must do it for all possible remainders. Even in the case, like you can eliminate the evens very quickly. They can be gone from there quickly because you can say they're not prime in this example.
So I think,
Okay?
so if I understand this correctly,
Who's
there's,
talking to me?
this is Britain.
Okay.
This is about the same question. There's some cases of those remainders that are just impossible.
Right.
And there's some cases of the remainders that actually make the proposition true.
Yes.
And there's no cases that are possible that make the proposition false. Is that correct? So there's no cases where there's a remainder that is a possible outcome that would cause the proposition to be false.
Now be careful. What that says is if it's a prime number greater than 3, it has a square of the form 12k plus 1. So you're starting out with the hypothesis that it's a prime number greater than 3. It does not say the converse. It doesn't say that all integers whose squares of the form 12k plus 1 are prime.
Right.
That is not what it says.
Right. But what I'm saying is just that, so we go through all of the possible,
Yes.
We use the division theorem and go through all the possible outcomes of dividing by 6. And we
Yes.
show that some of those outcomes aren't possible. There's no possible way to like get that remainder like a +2 or +3.
The key here, remember, is that you've got to have this 12k here. And if you were to divide by something other than 6, would you have a 12k? See, in each of these cases, when you do the multiplication, you can factor out 12 times an integer plus a remainder. And that remainder is always going to be, less than, well, if you divide by 6, what we have is if it's 5, it's 25. So that's less than 2 times 12. It's only one more than 2 times 12 plus 1. So I can factor 12 out of stuff, and then I have a remainder that's small enough to count. Okay?
Can I just ask a really quick clarification? Would 6 be the smallest value of b that we would choose in that case?
Yeah. Because if I chose 2, then I'd just have zeros and ones. I'd never get a 12 for anything. If I chose 3, I'd have 6s and I'd never get to 12. Okay. If I chose 4, I'd have a remainder of like 16. How am I going to get 12s out of that? Okay. So you can work your way up to needing a 6 so that you can get, when you do the square, you end up with a 6 somehow, at least, or something that you can get in terms of 12k plus something else, where that's smaller, okay? Where it's a constant that's small.
Great, that was very helpful. Thank you.
All right, I guess it's time to get going. All right, so what we've done is we've talked about direct proofs. We've talked about indirect proofs. So indirect proofs, like contrapositive and contradiction, are ones that what you turn around is, for the contrapositive, what you do is make the statement. Remember, the contrapositive says if you're trying to prove P implies Q, then the contrapositive is not Q implies not P. And then you do a direct proof of the contrapositive. Contrapos, not contradiction. Okay? Now, the contradiction, you're trying to prove the negative of what you want. So if you have P implies Q, then the contradiction of P implies Q is P and not Q is what you assume to start with. Okay, that's where you say assume or suppose. And then you go through and show that's impossible. And that's an indirect proof. By cases, the division theorem is really handy. That's how you get a lot of cases, is the division theorem. Induction. Induction is a type of direct proof. Now, someone asked, why can't I do n and then prove it's true for n minus 1? And I thought of what I considered to be a great example, that when you're building a house, you start with the basement and work your way to the upper floors. You can't start with the upper floors and work your way back to the basement. You don't have any foundation to grasp it on. So always remember, you go from the bottom up. It is also the case, you have to remember that if you assume everything is true for n, the predicate is true for n minus 1, then you prove it for n. You can also assume the predicate is true for n and prove it for n plus 1 if that's an easier way to do it. It means exactly the same thing. Okay, and then the last thing I say for induction, use the framework. Remember, the framework is you make your predicate and say what you want to prove in terms of the predicate and what are the cases, the base case and larger than or equal to whatever. You show it's true for the base case or cases, depending on what you need. You state the hypothesis, the induction hypothesis, and then you prove the next case. Okay. And the pigeonhole property. Okay. So here's an example. Prove no perfect square is of the form 3k plus 2. Give it a try. I give you the hint. It's another contradiction. So tell me what I should assume or suppose. What would be my contradictory supposition?
There's a perfect square that is of the form 3k plus 2.
Sure. So we say suppose n is a perfect square and n is equal to 3k plus 2. That's the first part of it. So as a perfect square, sorry about that. Don't know how I got there. Okay. So then, since it's a perfect square, since n is a perfect square, n is equal to m squared for some m in z. And that's the definition of perfect square. All right, now we use the division theorem. M is equal to 3k plus r, 0 less than or equal to r less than 3 for some k in z.
Should we use L instead of K since K was already
Sorry,
present
what?
in the... Should we use a different integer in the breakdown for M
Absolutely,
instead of K?
absolutely. I'm so used to using k. No, this part is k. That's the assertion. This one we should use that's different right here. Thank you. Let's say that's 3q plus r. How's that? Better? Thank you. All right. In that case, m squared is equal to 9q squared plus 6qr plus r squared. Okay, remember, we're going to have to factor out a 3 to show that it's impossible. So here's the first case, r equals 0. So if r equals 0, then n equal to m squared is equal to 3 times 3q squared, which is not equal to 3k plus 2. So that's a contradiction. Can't happen. You have to say those words. R equals 1, then n is equal to m squared, which is equal to 3 times 3q squared plus 2q plus 1. Well, that's a k, but that's a plus 1. That's a contradiction. Okay, now you have to say all these things. I'm not doing that so we can get through more examples. Let me just do this case here. Then this is more interesting. N is equal to m squared, which is 3 times 3q squared plus 6, and that's r is 2, that's 12, that's plus 4q plus 4, which is equal to 3 times 3q squared plus 4q plus 1 plus 1. And that's C. And that's a contradiction. So we have shown n cannot be a perfect square. And have form 3k plus 2. Okay, Grant.
Yeah, I was actually just wondering, does that star mean contradiction in proofs?
This? No, that's what I'm doing. You have to say that's a contradiction.
Okay.
And you have to say, you have to have more details here. So you have to go and say, well, that's equal to 3c plus 1, where c, all the rest of it. You need to have that to get full credit. David.
Could you do an even or odd proof for this or no?
Well, you're going to have a 2 there. You can't do an even or odd because it disappears. Okay. Is k an integer? Absolutely. Everything's an integer here.
If a proof problem does not state some other domain, can we assume that it's talking about integers?
What I would say, if a proof problem doesn't say anything, ask a question on Piazza, because I'm going to try and not let that happen on this quiz.
Okay.
I will send myself reminders to double check that. Okay? If it does occur, ask to make sure. You're probably right, but double check. Okay, we have time for here's a true or false. And this is going to take too much time. I want to go for some of the examples, but let's give an example here. If X or Y is odd, then X times Y is odd. Is that true or false?
False.
Why?
I don't know. 2 times 3 is even, and 3
That's
is odd.
perfect. Done. Yes. It is also the case that an even times an odd is even. What about if I said if X and Y is odd, then X times Y is odd?
True.
That would be true. Odd times odd is odd. 3 times 5 is 15 for an example. But you could prove it, couldn't you?
Yeah.
Let's see. N is even if and only if n squared is even.
True.
True. We have talked about this. So that is 2 ways. You would have to prove if n is even, then n squared is even. That's subproof 1. Subproof 2 is if n squared is even, then n is even. Okay, this one's pretty straightforward. That's a direct proof. This one, we already said, that's a contrapositive proof. When you have it, and if and only if, you have to go both directions on the proof. Okay. Too far. Yeah. How would you prove, if you weren't told to use a technique, how would you prove if n is an integer, then n squared plus 3n plus 4 is even?
Just find a way to factor out a 2, I guess.
Can't hear you. You've got to speak up, please.
My initial thought is to prove it by cases with n being even and odd, I think.
That's very good. That's a direct proof with cases. Very good. That uses the division theorem, even and odd. Okay, what about number 2? If 7x plus 9 is even, then x is odd. What would
Probably
you
do a counter-positive proof.
That's possible, but a direct proof would be simpler in this case. How would you do a direct proof?
I guess if we know the form of even, I guess we could say like 7x plus 9 equals 2k or something, and then sort of algebraically rework it to.
Yeah, you could say, well, then 7x plus 9 equals 2, that's an x, equals 2a. Then what?
And solve for x.
Yeah, you can't solve for x very well. That's not going to be right. I think she was right. I take it back. Bad. So what would the contrapositive be? Come back, Vista. Come back. What's the contrapositive?
Yeah, it would be x is even, then 7x plus 9 is odd.
Much easier proof. You're right, 100%. Good job. If P or Q, then R, what would you prove?
I would go by cases.
I'm sorry?
My first instinct is to go by cases, depending on the truth value of P or Q.
What would you say? Actually, what you say is if P, then R, or if Q, then R. So you're right, you prove one or the other. Okay, good job. What's our next one here? Here's a new one. Okay, sequence. Let a sequence of number a sub n be given by the recurrence relation a sub k is equal to a sub k minus 1 plus 2k for k greater than or equal to 2, greater than or equal to 2, and a1 is equal to 2. Prove that an is equal to n times n plus 1. What would you do to start that? What does that yell at you? What kind of proof is that?
Induction.
What?
Induction.
Induction. Okay, so we're going to let b sub n be equal to n times n plus 1. And a sub n is given, so our predicate is that a sub n is equal to b sub n for n greater than or equal to 1, because that's what this says here. That's our predicate. So we prove the base case. For n equal 1, p of 1 is what we want to prove is true. So what do we have? We have that a1 is equal to 2. That's given to us. There's no computation. And b1 is equal to 1 times 2, or 2. So P1 is true. Okay. Induction hypothesis. Assume P sub n minus 1 is true. That is that a sub n minus 1 is equal to b sub n minus 1. Now we have to prove a sub n is b sub n. So what we say a sub n is equal to a sub n minus 1 plus 2n. But that's equal to b sub n minus 1 plus 2n, and that's by the induction hypothesis. Okay, we're not done yet. So what's b sub n minus 1? That's equal to n minus 1 times n minus 1 plus 1, which is equal to n minus 1 times n. Oops. Plus 2n, which is equal to n minus 1 times n plus 2n, which is equal to, did I have that right? I hope so. N squared minus n plus 2n, which is equal to n squared plus n, which is equal to n times n plus 1, which is equal to bn. So we follow.
Do we have to list distributivity when we pull out n?
Yes, right there. That's the distrib property. Okay. So then your conclusion, a n equal b n for n greater than or equal to 1. Okay. These will be online later today. Remember, review sessions Monday at noon, Tuesday at 5. We will try and stream and record them. Homework is due tomorrow night, 11:59 p.m. Someone asked, what about getting the quizzes back? I'm sorry, we cannot get it back. As I announced, we cannot have it back today. And we're going to still try and have it back to you tomorrow. Let's say your quizzes as a whole were not as bad as some of you thought, but they weren't as good as I hoped. So I want to go through them and look at them more closely before I give them back to you. All right. Are there any questions? Class is over. People can leave. If you want to ask me anything, you can stay and ask.
For grading on the quizzes, will like where we made a mistake or where we lost points be pointed out, or are we just
Yes.
Awesome.
Yes. Grade scope is very nice. It says exactly where you lost points. And sometimes there are comments in addition to just the point pull off for what it is. If it's still unclear to you, you can ask send in a message on Piazza, just asking about it. You can send it private to instructors if it's about your particular questions. Okay.
For proof by contradiction, if we're not given a statement in the form of an implication, proof by contradiction still works, right? We just have to negate the original statement.
Yeah, if you're not given an implication, contrapositives don't necessarily work, but contradiction does. Remember, sometimes it's not phrased per se as an implication, but we've spent time being able to phrase something as an implication when it's an implied implication. So you have to be careful and make sure, is it really not an implication? Like saying the square root of 2 is irrational is definitely not an implication. No way. But sometimes something is an implication, even though on first glance, there's no if then. The words that are used, like whenever something is true, then something else is true. That's an if then statement too. So be careful. Okay.
Thank you.
Any other questions?
I had one question on the proof by contradictions.
Yes.
Specifically when there are more than one case.
Yes.
Since we're just trying to prove a contradiction, can we just find one case that is a contradiction and say, therefore it is a contradiction?
It depends. If the proof says that you want to prove something is true for all cases, then showing a contradiction for one case is fine. If you're asked to show there exists a case for which something is true, then a contradiction of one case is not it. You have to prove there are no cases for which it's true. So there the question is, does it say for all or there exists?
Okay, yeah, that makes sense. Thank you.
Okay. If
Thanks.
no more questions, I'll say bye-bye. I'll see you Tuesday.